Hi. This talk is called Infrastructure as Code Might Be Literally Impossible. Hi, I'm Joe. I like computers. I once had a blog called timetobleed.com. I don't have that much time to blog anymore, but I used to blog a lot about like operating systems, device drivers, security bugs, like really low-level stuff. So if you enjoy this talk, there's lots of other stuff similar to this on my blog, so you might want to check it out later. Occasionally, I use Twitter, and on Twitter, my Twitter handle is just Joe Damato. I'm the CEO and founder of a company called Package Cloud, and what Package Cloud does is it allows you to sort of store and manage your Debian, RPM, RubyGem, and Python packages really easily with some security stuff and automation stuff. It's pretty dope. So if you have any problems with that sort of stuff, you should check us out. And in this talk today, I'm going to show some examples of why like none of the existing open source packaging stuff actually works, and why you should definitely not use any of it. If you want to follow along, the slides are up on the blog, just blog.packagecloud.io. You can check it out and follow along on your laptop if you want. Okay, so infrastructure as code might be impossible because nothing works. So perhaps to like understand this, maybe we should start with understanding at a high level, right? Like what is code, and then relate that back to infrastructure code and see if we can use that to drive home this idea that infrastructure code is just impossible. So to that effect, right, like what is code? So code makes computer, with a capital C, do complicated stuff in small steps. So each small step is usually made up of a keyword and some other stuff. And so keywords in programming languages let you use your computer. And different languages have different trade-offs. And some programming languages are difficult, and they are perceived to be difficult. And perception is reality, I guess. And we're going to talk more about this idea of perception in a bit. But some languages that are difficult and are also perceived to be difficult are languages like assembly, C, C++, and so on. And because they are difficult languages to use, and they are also perceived by their users to be difficult, most people try to use them defensively. And so what do I mean by using a programming language defensively? What I mean is, if you're going to write code in like assembly, C, or C++, you need to be really careful about the code you're writing to make sure that it does what you expect it to do, and that when it fails in some way that you can actually control. And that brings us to our first of many story times throughout this talk. This story time is a story involving two of my friends, the Opteron Revision E and pre-release Revision F processor, and a program called MySQL that some of you might be familiar with. So the Opteron CPU is just sort of a normal run-of-the-mill AMD CPU. It's just a regular like x86 CPU, and like most other x86 CPUs, it comes with a set of CPU instructions that are atomic. And these instructions are actually used by operating system designers, systems programmers, and so on to build higher level synchronization primitives like mutexes and semaphores, readers, writers, locks, and stuff like that, right? So if you ever use the mutex to prevent multiple threads from running the same piece of code at the same time, like deep down beneath all of the code is like an instruction running on your CPU that's guaranteed to execute atomically. And the interesting thing about the Opteron Revision E and pre-release Revision F processors is that both of those processors, the atomic instructions aren't actually atomic. And that's kind of bad, right? Like if you were expecting to write a piece of code that would only be executed by one thread at a time, and you're like, okay, I'm going to use this instruction on my CPU to do that, like you couldn't because the CPU is actually broken, right? The hardware is just broken, and there's just not really that much you can do about it. And that's sort of where MySQL comes into the picture, right? Like a lot of people hate on MySQL. They think that MySQL is difficult to use, it's difficult to manage, difficult to deploy, difficult to understand. I think MySQL is actually pretty dope. And the reason why I think it's dope is because when these processors got released, MySQL was running, and MySQL was written in such a way that when this CPU bug was triggered, and when multiple threads that were supposed to not run concurrently ended up running concurrently, instead of MySQL just like exploding and crashing, right, it raised a bunch of assertions and said, hey, like something's not right. And it turns out that like those assertions made it really easy for people to track down and understand later on that there was an actual bug in the hardware. And I think that that's like pretty interesting, right? Like the idea that you can write software in such a way that it's defensive enough that it can prevent you from like that it can prevent like your entire world from shattering when like the physical hardware you're using is like actually just broken. So anyway, back to the whole thing about languages, right? Like, that's like sort of a thing about like languages, right? Like you have like languages that are perceived as being easy languages, but are actually terribly difficult and or impossible languages to use. So here's an example of like languages that I think are perceived as easy, but are actually impossible. Those languages are languages like Ruby, Perl, Bash, Python, and so on. Right, like these languages, like people look at them and they're like, these are dope, right? Like I'm a beginner, I can like write Python today, right? But it turns out that like writing Python or writing Ruby or writing Perl or writing Bash is like impossible. It's like way harder than writing assembly. And like as an aside, I actually think that in order to write like good Ruby code or to write like really fast or performant Ruby code, you actually have to be an expert in C. But that's actually part of a different talk that I'm not giving today. And that talk is called High-Level Languages Don't Exist. But anyway, these languages are it's hard or impossible to use any of those languages I mentioned previously defensively enough, right? Because like you only have a certain amount of control over what you're doing, and there's layers of complexity underneath you that are doing things that like you actually don't have the tools to control, which in some cases is good, but in some cases is bad. And this brings us to sort of our next story time. So it's two interesting stories from the Ruby VM implementation. So the first is about Ruby VM seg faults. So if you've ever run a Ruby VM in production and you've thrown like a substantial amount of traffic at it, perhaps you've seen the Ruby VM seg fault from time to time. And there are many reasons why the Ruby VM will seg fault. But one of the major reasons why the Ruby VM seg faults from time to time is due to a bug in the garbage collector and the object allocator. And basically what ends up happening at a high level is that you have objects that are in use by your Ruby programs. The GC runs, but the GC can't see these objects that you're currently using due to like a really, really nuanced bug in the object allocator. And so the GC doesn't see this object you're still using, and then it runs its like cleanup phase to go and free everything, and it accidentally will free objects that you're still using in your program. So then later when you go to use that object, right, the Ruby VM explodes because like that object is no longer valid because it accidentally freed it even though you were still using it. And there's really not that much you can do about that, and I'm going to show some interesting bugs like around that shortly, but it's just this idea that like you have this object that you were using happily, and then like out of nowhere, GC just like ruined your life underneath that. And sort of another story like in the same vein is this whole idea about how threading worked in the Ruby VM. So the threading implementation has changed a bunch over the years. Previously, it was implemented with something called green threads, which is a way of implementing a threading algorithm or a threading sort of subsystem solely in userland in a way that like the operating system doesn't know anything about. And it's like a perfectly valid way to build a threading system if you just care about I/O concurrency. But due to a like really, really like obscure bug in the Ruby configuration system, there was a time when you would use like a default Ruby from your distribution, or you would just compile Ruby, and you would lose about like 30 to 60% of your performance just because the wrong system call was chosen during like running /configure in Ruby. And I'm going to talk more about this bug later and like sort of a lot of the interesting side effects it's had since then. But the reason why I mention these is not to like bash Ruby or anything. Like I think Ruby's great, I use it a lot, but it's just to like have this idea that, right, like these bugs are like really, really insidious. And what I mean is just that like they're just really difficult bugs to understand, they're difficult bugs to debug, they're difficult bugs to fix. And even after you fix them, right, like deploying changes for this type of stuff is hard, it's risky, it's just painful. Right, so like thus, right, like your code does things outside of your reference frame. And it does that unless you've read every single line of code like all the way down to the bottom, which is actually literally impossible. Like there's no way you could do that, right? You'd have to read like your entire app, your framework, your VM, your operating system, your device drivers, your firmware, and it's like literally impossible. Like no human being could ever do that. So, okay. So how does this relate to infrastructure code? Well, infrastructure code makes your computer do complicated stuff in small steps too. And infrastructure code has like really, really high level keywords. So here's an example of some infrastructure code, right? This is like an example from Chef, right? I'm installing some package at this version, right? And this is going to do a whole bunch of stuff, underneath. It's going to like find the package manager, install this package, do all this other stuff. And here's a similar example from Puppet, right? You're just going to install the package on your computer. What if I told you that your infrastructure code operates outside of your reference frame as well? Meaning that unless you've read every single line of everything all the way down to the bottom, including your configuration management system and everything it depends on, which you obviously haven't done because that's literally impossible, it's doing stuff that you don't understand and things you can't control. Okay, so some things you probably didn't know about computers. What if I told you that an MRI bug once made Puppet peg CPU usage very, very high, so high that, in fact, Puppet was actually unusable? It turns out that this actually happened, and the reason why it happened is due to a system call called sigprocmask. And sigprocmask is actually called via a set of other system calls, setContext and getContext. And as I was talking before about sort of like the MRI threading implementation, in order to build green threads on a system, you typically use a set of system calls. One set that you can use is setContext and getContext, and the Ruby VM uses them for exception handling and for implementing this sort of userland threading library. And it turns out that these set of system calls, if you use them, they call sigprocmask underneath to sort of save and restore the signal mask of the thing that's executing. And if you do exception handling, which you're probably doing a lot of because you're writing Ruby code, or you have like a lot of threads that are running and you're constantly switching between them, you can end up eating so much CPU time by just entering and exiting the kernel to save and restore the signal mask that you can reduce the actual speed of your Ruby code from running down to a crawl to a point where it's like basically unusable. And here's a report from a Puppet sort of bug report, right? The Puppet process spends 40 to 60% of its time in system time, which lengthens the time a single Puppet run takes from a few minutes to greater than 20 minutes. So it's more than like a 20x increase in execution time, all because of like a small, tiny, obscure bug in the configuration script when Ruby was being compiled initially. So like, how do you even solve that, right? Like, well, one way is like, so like I wrote a fix for this bug, but that fix was never accepted upstream because of open source politics. Hi. You can find more information about this bug on my blog if you're curious. And a friend of mine, he's working at a huge company. They're running Puppet on like tens of thousands of computers. And he told me that without this patch that he like copied and pasted from my blog, right, they couldn't run Puppet on any of their machines, which is pretty weird if you think about it, because like this dude, he's like running this program on like whatever, 100,000 computers or whatever, and he's literally copying and pasting a patch from timetobleed.com straight into his like infrastructure. And so like for all he knows, I'm currently mining Bitcoin on all of his computers, right? So hi. So then is it a coincidence that you can find a blog post like this on the Puppet blog? We're working on rebuilding our entire client-side technology stack so it takes fewer resources, runs faster, and is more maintainable. Supposedly, and that's actually the correct spelling of that word, they are supposedly rebuilding some or all of their client-side stuff in C++ and moving away from Ruby. I don't know, like doesn't sound like a coincidence to me, right? I mean, and I'm not just like I'm not trying to like bash on any individual technology or individual system, right? Like I use a lot of these systems and I think they're really important, but I think like I'm just trying to highlight like this general trend and this idea. So similarly, there's a bug filed against a Chef program called OHI. And if you haven't used Chef before, OHI is just this program that runs on your computer that gathers information about the system. So it'll gather information like the host name or the operating system kernel, stuff like that you can use that information in your Chef recipes. So there's a bug filed against this program, and it says that OHI crashes on Solaris 11 and Ubuntu 12.04 in some Ruby file when it runs popen4. It turns out that the reason why it crashes is due to that bug I was just discussing earlier around the object allocator in the GC system, right? Like OHI is doing something, it has like this object it's using happily, and then a GC run happens, and then it tries to use that object to do something, and like the whole world shatters beneath it, and like the Chef run just like dies, right? And like that's actually like kind of scary, right? Like if you're running Chef and like you're mutating your infrastructure, and like suddenly like your Chef process just like explodes underneath you, that's like probably bad, right? Like who knows like what state your system is in, like whether or not the things you were doing were idempotent, like I don't know, right? Like you're basically left with like a plate of spaghetti and it's like, here you go, I don't know. And so like, what's the workaround for that, right? Like the workaround for that like Chef did was like, they just disable the garbage collector when they run this like small piece of code, and then after it's done running, they re-enable the garbage collector, right? Like that's pretty interesting, I think. Like when I saw that workaround, like I don't know, like I thought that was like really, really interesting that the workaround is like literally to disable a major feature of the language so that like your code won't shatter the world like when it's running. And I don't know, like I just think that there's just like something interesting about that. And it doesn't stop there. So what if I told you that it's literally impossible to install a program securely on pretty much every version of Linux? Surely at least one person would stand up in the room and start screaming something about package management systems having GPG. To which I would tell you, no. It turns out that none of the package management systems actually use GPG correctly. So like, Yum and GPG, the TLDR here is that it just doesn't work most of the time, and it's like actually nearly impossible to get it working. So if you're not familiar with like Red Hat or CentOS or Fedora-based systems, Yum is sort of the equivalent of apt-get. You can use it to install and remove programs. Which leads me to the next story time. And the first friend of mine who's in this story is a friend by the name of pygpgme. So pygpgme is a program that's written in Python that if you're using a Yum repository that has GPG signatures associated with it, right? Like, I don't know if any of you have installed command line software that you got off of a vendor's website that it's like, hey, import our GPG key and then like install this repository and install this program. Well, it turns out that if you don't install pygpgme, none of the signatures are going to get verified, and Yum is going to silently ignore them and install the package anyway. So it just doesn't matter if you import the GPG key because it's not going to get used. You need to install this program. And if you think back to the times that you've copied and pasted stuff off of a vendor's website, like how many times have you read like an instruction that's like install pygpgme? Like I never have. I don't know, right? Like it's probably pretty rare. My next friend, an interesting story behind this friend as well, is repo GPG check. So there's several layers of GPG signatures as far as like Yum repositories and RPM packages go. And one layer of GPG signatures are GPG signatures on the packages themselves, right? So like, was this package generated by the person I think generated it? And then the next layer of GPG signature is a GPG signature on the repository metadata, right? Like, was this repository itself, this collection of packages, generated by the person I think it was generated by? So repo GPG check is like pretty much never used in the wild. I mean, we use it by default on all the repositories that we generate on Package Cloud, but most people have never heard of repo GPG check, and a lot of people sort of like have this confusion about like, what does GPG check actually mean? What is actually being checked? And it's important to keep in mind that there's two layers of signatures, on the packages and on the metadata. And if you're signing packages, you should be sure to use GPG v3 signatures, not v4 signatures. Why? Well, there's a fun story behind that one, but it turns out that RPM is actually unable to verify GPG v4 signatures. So the solution for this is to always use GPG v3, which is like, you're thinking like, it's probably not too bad, right? Like, what do I got to do? Just like use some command line thing. All you need is that, and which is fine because like it's documented here in my presentation, and you can just copy and paste that like into a configuration file on your computer, right? Like, other than here, I don't know like that many other places where it's documented. So
that's for going directly into a spec file, right?
this is this you would put into you could put it into a spec file directly, or you could put it into like your RPM macros in your home directory. And so like that's like pretty dope, right? Like there's this thing, and like who knows where it's documented, and like you copy and paste this in your computer. So hi to that one. And there's another option called Ssl Verify. So Ssl Verify, like as you would probably expect if like you've been paying attention so far, Ssl Verify is actually set to disabled for a lot of the like early versions of Yum. So like Yum on CentOS 5, which is still alive and kicking, and some versions of CentOS 6 actually have Ssl Verify defaulted to off. So if you're telling people to install your Yum repo, you should tell them to set Ssl Verify to true, because verifying SSL certificates is important. So cool, right? So like, apps can't get away free on this one either. It turns out that apt and GPG, it doesn't work most of the time either, and it's basically impossible to get working. So story time on this guy too. DebSigs versus dpackagesig. There's like a lot of people that publish software that are super into using GPG. And the thing is that like using GPG for Debian packages is just like, actually, there's just no point. And there's two programs you can use to sign your deb packages, debsigs and dpackagesig. One of them works with apt, the other one doesn't, and neither of them produce signatures that can be verified by the other. So do whatever you want. GPG signing deb packages is pointless. Because even if you do use the one that's supported by apt, how many, like, I'm sure you've probably seen people say, hey, like, this is my Debian repo, right? Like, my packages are signed, import my GPG key, right? Did they ever give you an XML policy document that you're supposed to use on your computer to verify the GPG signature? Probably not. And the reason why I know that is because it's basically impossible to find documentation on how to even build this XML policy document. I built one because I wanted to see if it will work. Looks like that. It turns out that you need to have the GPG key ID in the path, but not part of the file name for some reason. So you need to generate a file like this if you actually want your Debian packages to have their signatures verified. And no one's going to do this, like, just like letting you know, like literally no one's going to do that. And no one's going to debug it when it breaks. And when I say no one, I mean like not even Ubuntu does this, because it's just like this is just not like a thing you can tell a user to do, right? Oh, and a couple other things. The GPG implementation on both apt and yum, they're both vulnerable to replay attacks. Neither of them deal with key revocation, and they're vulnerable to several other GPG-related attacks, making them like literally completely useless. These are just some of the infinity reasons why you shouldn't do it yourself. So what if I told you though that like something like really important stopped working, right? Like maybe you'd believe me that infrastructure as code is impossible. So what if I told you that the CA certificate bundle that you use to verify certificates one time accidentally revoked AWS's SSL CA? Before I explain that though, I think that we should take a moment to have a periodic reminder that the trusted list of CA certificates come from the following URL and are used by the entire internet: curl.hacks.se. So anyway, there's a tool called Bento that a lot of people use to generate vagrant images, and this is pretty useful if you're using something like Kitchen to run tests on your chef or Puppet recipes or whatever. So ops code CentOS 511, which is just an image of CentOS 511 that the chef folks generate. That image that was generated on or around February 23rd, 2015, updated the CA cert bundle, and they pulled it directly from hacks.se, which is where everyone else gets it from. But it turns out that that instant when they pulled it down, it had accidentally pulled down a bundle that had revoked AWS's root CA, which means that like if you were doing anything that needed to talk to AWS at all, you couldn't unless you weren't verifying certificates, which you probably want to be doing, right? So you would download this image, you would like boot it and like use it, and suddenly you just couldn't talk to AWS at all. And there was sort of a lot of like going back and forth as to like who's at fault here, like where did this problem come from, right? And here's an email from the curl.hacks folks. They said, hey, we in the curl project didn't anticipate anything of this. We get the data from the Mozilla project and they changed the properties. We've run the same script daily since a long time. One day the output changed to this. And you were no longer able to use S3 or EC2 or anything anymore. And so, we ended up with like a whole bunch of these vagrant images floating around where you can't access anything on AWS. And you can read more about this bug and sort of the debugging process on Chef's blog. And they have a lot of cool examples. I worked really closely with them to help them debug this. And PS, by the way, like debugging OpenSSL is like, or debugging SSL bugs in general is just like really, really, really hard. By the way, quick thing. I think there's sort of like this underlying concept like that I've been thinking a lot about when I was like working on this talk and thinking through what I was going to say today. And like one of the things underneath all that is this idea of like cognitive load, right? Like cognitive load refers to like the total amount of mental effort being used in the working memory, right? So like at some point you have to wonder, when does all of this stuff just become too much, right? Like what human being out there can remember like a never-ending stream of atrocities when they're trying to like just get something working, right? They're just trying to like do their job. A lot of times you hear like in open source, like, hey, we don't really need documentation, there's no documentation, right? Like just read the code. It turns out that like just reading the code is literally impossible because you need to read millions of lines of code. It's just like so much cognitive load, it's just impossible to like actually deal with as a single human being. And to this effect, right, I was talking to a friend of mine, he works at a pretty big company and they use Chef for everything, and he was telling me, people changing our Chef recipes to make something work for them and then accidentally breaking everyone else's stuff is practically constant at my company right now. And I think that this has a lot to do with like this idea of cognitive load, right? Like you can't keep like the entire state of the system in your brain at one time because it's just like too complex, right? Like any company that's as big as my friend's company is gonna have like lots of moving pieces, and there's just like no way one person can keep it all on their brain at once. And so like, like you're thinking about this, I was thinking a lot about this problem, right? Like people are constantly changing things are constantly breaking, like everyone's like trying to move really fast, people have unrealistic deadlines, right? Like why do these things happen? I don't know, but like this is probably all part of a different talk that I'm also not giving today called The Effect of Capitalism on Computing. Anyway, what if I told you that you can do a denial of service attack against a computer system just with apt and yum metadata? And it's actually a pretty easy attack. It's kind of funny. When apt and yum request metadata, just reply with a never-ending file, and then you'll fill up that person's hard disk, and then their computer will explode. But you might be thinking like, hey, who's going to do that, right? Like, I'm not an official mirror. I'm just like some dude running like a VPS or whatever. I'm just some person using a VPS. Like, who's going to trust me and run apt-get or apt-get update against my server and fill up their hard drive and have a really bad day, right? Like, I'm not an official mirror, right? Like, and if you've been following what I've been saying throughout this entire talk, the answer to this question is actually kind of obvious. It turns out that the Debian and CentOS, it turns out there are a bunch of researchers from universities, security researchers, had this idea. They're like, hey, what if we tried to like set up a completely fraudulent apt and yum mirror that we told the projects was like a real mirror, right? Like they set up a directory on a server, right? Like, so these guys went all the way, by the way. They like created a shell corporation in like, I don't know, like it's on some random island in the Caribbean and stuff. Like they had like a fake company set up. And they racked a server somewhere, and they emailed like Debian and CentOS and Fedora and all these open source projects, and they were like, hey, like here's a directory of stuff that like I'm exposing to the internet. Like this is an official mirror of you guys. How do we get added to the mirror rotation so that when people install stuff on their computer, it'll come from us? And the Debian and CentOS folks listed the mirror within a few hours, and the Fedora people listed the mirror in minutes. Right, so no one even bothered to verify, like, hey, like, is this mirror that we're adding to the rotation from which like everyone installs their software, is this real, or is all this stuff just like Trojaned or hacked or like Bitcoin mining stuff? Like, what even is this stuff? And the answer is like no one knows, right? Like, I mean, people get all up in arms about like, it depends like how deep down the conspiracy theory rabbit hole you go, but like you can go pretty deep, and you can like read these like really interesting articles by people who say that like, different security organizations or different intelligence communities already know about bugs in libSSL, and like all these bugs that we're finding in patching now, like the CIA or whoever already knew about these bugs a long time ago, and that's how like we steal intelligence from other countries or whatever. The thing is like none of that even matters. Like who cares like if libSSL is broken? Like you can't even install a program on your computer to begin with. It's like it doesn't even matter if libSSL is broken. Like if I can set up a Fedora mirror in like 2 minutes without anyone verifying me, like by creating a shell company in the Caribbean, it just doesn't, like nothing else matters. Like it's just pointless.
Well, then the question is, how many mirrors does the CIA have set up?
Yeah, exactly, right? Like I mean, so I don't personally believe it, like any of that like really intense conspiracy theory stuff, but like that's the thing, right? Like if someone can just create a mirror in like 5 minutes that's like all lies, then anyone who's like actually trying to like do serious damage can like sit down and think of a much better plan than that, right? So like, maybe like at this point, like you're probably pretty sad about things, and like I don't blame you, but like the thing is it's so good it just gets better. What if I told you that the programs that are responsible for actually generating the metadata that the operating systems use when they publish their package repositories? What if I told you that those tools accidentally output incorrect metadata sometimes? In fact, Create Repo, which is the tool you use to generate Yum repositories, outputs incorrect metadata pretty regularly. It's because of a bug in a package called RPM utils, which is written in Python, and it sort of like a really interesting, it could have actually been a typo. I mean, who knows, right? Like RPM uses a Python function called find, instead of using rfind, which is like a reverse find to start from the end of the string and go the other way, when splitting package version strings, right? So version strings with 2 hyphens in them are split on the first hyphen, not the second, yielding metadata that has version numbers that are actually incorrect, right? So you end up with actual incorrect package metadata. So like if you were using one of these packages and you needed to upgrade one of them and you wanted to install one of them on your system, right? And you're like expecting Yum to figure out that, hey, this one that I have is newer than the one that's out there, use mine instead, right? Like you can't, because like the metadata that's been published is actually just wrong, right? There's no way for Yum to compare it because it's just wrong. And like this is actually live in the official mirrors like right now. I ran a script that did like an analysis of the existing packages, and I think it was something like maybe 30 packages have incorrect metadata that I could find. So like, it's open source, like what do? You file a bug, right? So I filed the bug against RPM utils package, and the maintainer basically said like, I'm never gonna fix this. Because in the maintainer's mind, there's only one way to generate an RPM package, and that way is using like the RPM build toolchain. And his claim is that the RPM build toolchain won't let you build packages that have versions that are wrong. Because in this person's mind, he can't imagine a world in which someone would use a different tool. Like he can't imagine someone using like FPM or some other tool instead to generate an RPM package. So there's not really that much you can do, right? Like it's just broken, and like, here we are. So these are all cool stories, but what gives, right? I mean, people are using infrastructure as code today though, right? So what's going on here? Well, I mean, indeed people are, with varying levels of success, and in many cases great pain, depending on exactly what you're doing and how you're doing it. And I don't know, I've experienced this pain personally, right? Like I do a lot of the ops stuff for my like small internet service. So like I know, like, I kind of like anyone out there who's felt this pain, like I know where you're coming from because I deal with it too, right? So like in my opinion, I just have 5 quick opinions, then I'm done here. Opinion number 1 is I don't really think like we're gonna be able to have this like truly reproducible infrastructure until we figure out better ways of building computer systems. I don't know if any of you guys went to the talk yesterday about the secure programming language, about like building a programming language with security baked in. Like I think like stuff like that's like super interesting, and I think that probably people who work in industry need to pay more attention to people doing like research stuff like that, or PhDs working on stuff like that, because that's sort of like the only way out of this mess, really, is by thinking about problems that way and sort of funding those efforts and trying to figure out like how can we take ideas from academia and build them into industry in ways that make sense, right? Opinion number 2 here is just that like each time you move to a high level of abstraction, you need to know more stuff. So like maybe cutting out some layers in between can make this more easily solvable. Maybe it can, maybe it can't. I don't know, right? And I think there have been like a lot of attempts over the years to sort of simplify the like programming and the compute stack, and it kind of goes back to just like I don't know, like I think like a lot of this goes back to this idea that I've been formulating, that the idea of like a full stack engineer, like it's just not like it just doesn't exist anymore, because there's just too many layers of complexity throughout the entire system that it's impossible for any one person to know how it all works. And that would probably be okay if you could build systems in such a way that like you could provably say that this part of the system doesn't have any defects. And like right now you just can't, because of like manufacturing processes, the current way we build software. Like I don't know really what the answer is, but what I can tell you is that like complexity increases as you add more layers of abstraction, and it makes things like those bugs that I mentioned in Puppet and Chef possible, because you have like this little tiny bug in a configure script somewhere that no one even knows about that ends up preventing Puppet from running on your computer, right? Opinion number 3, like I just think this is sort of general, right? Like we need to be more honest and responsible about our choices and analysis of technology. I think that's just like sort of true across the board. A lot of people really like to use something because it's like new and shiny, but resisting that urge I think is a good idea if possible, because you never know, sort of like you might upgrade to the latest version of a program and like you're gonna get all these new features, but like who knows what kind of cool bugs you're gonna get. Opinion number 4, right? Like huge companies making billions of dollars on top of these software systems should take the initiative to invest in them and make them better. And I was curious, right? Like when I was looking at all these interesting apt bugs and Yum bugs, I was sort of curious, like, okay, like, so how many people are working on apt, right? Like, you know, like Canonical, it's a pretty big company, right? Like they have like all this like Ubuntu stuff they do. They have like a lot of people working on it. So they probably have like a lot of people working on apt, right? Like it's pretty important, right? I mean, like apt installs literally every single program and every single Ubuntu that's out there in the world. So presumably they have a bunch of people working on this. It turns out it's like one person who's working full time and like 2 college students who work on it part time. And like, I don't know, like it's tough. Like I think that like it's important to like look at these people and like really appreciate like what they've done and like how hard that they've worked. Because like there's no way that like, I mean, running a project like apt yourself, if you're just one person or like 2 people part time, is like probably impossible, right? And like, it kind of raises this question in my mind where it's like, like why don't like huge companies who rely on, who make billions of dollars from like these tools existing, like why don't they invest in like making them better, making them easier to work on, making them easier to maintain? And there's just like a ton of bugs in apt. I've blogged about lots of them, right? Like apt uses a compression format to compress repository metadata, and one compression format it uses is LZMA, which is typically represented with the .xz file extension. Their XZ decompressor doesn't work, so if you're using XZ metadata, you get like weird errors occasionally, not all the time. It's vulnerable to a bunch of really interesting replay attacks because they just use a single GPG keyring instead of having per repository GPG keyrings. I don't know, right? Like there's just like a lot of things floating around here. And I don't really know the answer, but I just think that there's like this pattern, right? Like I don't know if any of you remember reading that article about the guy in Germany who he's like the only maintainer of GPG, and he's been working on it, and like it came out like a couple years ago that this dude was like basically broke. And he's like, the only person in the world working on GPG, which so many people rely on for privacy, for security, for verifying stuff, right? And when everyone found out, hey, it's like a dude who's like about to go bankrupt from working on this, right? A bunch of companies stepped in and they were like, wait a minute, this is important. We should probably give this guy like some loot so he can like, eat while he works on GPG at least once a week. And I think there's a lot to be said there, right? Like I think there's lots of other open source projects that are really important but are like systematically undervalued. And again, I don't know what the answer is, right? Like I'm just one person in all this mess, but like I think there's something to that. And my opinion number 5 is, I don't think we've sort of really found the answer yet. I honestly like, despite the bugs and stuff that I've highlighted in my talk, I think that the stuff we have today is better than the stuff we had yesterday, right? Like I don't think it would be good to throw out all this stuff and go back to just writing like a bash script or whatever. But I don't really know what the answer is, right? Like I mean, I don't know if any of you use things like, like CI systems like, or like things like Kitchen CI or Beaker or whatever to like run tests on your infrastructure code. I mean, like that's an answer, right? Like you can just run tests on your infrastructure code too, but like it just feels weird. It's like how many layers of testing do you need to have, and like how long does it take to actually deploy changes, and like what are like the trade-offs between like shaving out this whole infrastructure in Kitchen CI versus just like hoping that it doesn't explode. And I don't know the answer, right? The answer is going to be different, for your company and like your economic goals and all that. But like, I think like in general, right? Like I think like the real answer is still out there somewhere. And I think that like, we probably need to think bigger about like where the direction of computing is going. And like, again, like looking to researchers and like to funding research efforts, understanding how to build systems that make sense. Anyway, that's all I have to say about computers. So if you guys have any questions, I'd love to try to answer them. And thanks a lot for stopping by and checking out my talk.
Can you just say that again? We're recording.
So when I apt add key, like Spotify and Chrome and Dropbox, they tell me to apt add key before I apt-get install their package, right?
Yeah.
Or their repo, right? What is it actually checking, if not?
So apt add key, what it does is it inserts the public GPG key into a single global GPG keyring, and it uses that key to check the GPG signatures on the repository metadata. But because they have a single global GPG keyring, there's a bunch of bugs around like man-in-the-middle attacks. It's a complicated attack, but even if you serve up your repository metadata over SSL and you give someone a GPG key they can use to verify it, if they use any other repository source that's over plaintext HTTP, like for example Ubuntu is all over plaintext HTTP, if an attacker knows that, they can go and they can sort of forge a bunch of, they can sort of capture, like, so like say Dropbox releases a version of Dropbox, right? You import the key, you import the repo, you're going well, and Dropbox releases a security advisory. They're like, hey, this package is broken or whatever. An attacker knows you're using Dropbox, right? They can snapshot, Dropbox's, Dropbox's like repository metadata, and then they can intercept your plain text HTTP connection to like Ubuntu, and they can replay that metadata back to you. And since you've imported the GPG key in a global keyring, even if they it'll like apt will say, okay, like this key is in the keyring, like install this package, it's fine. It's trying. So anyway, so sorry. The short answer to your question is that it's checking a global keyring. It's inserting the key into a global keyring, which is then checked against repository metadata. But the process in which it does that is vulnerable to like several layers of GPG attacks. So. All right, cool. I don't see any other questions, but if anyone wants to chat with me after, I'll be around. Thanks a lot for stopping by.